In this video, I'd like to explain how hydrologists estimate what is called the exceedance probability of an event based on a limited number of observations of that event. So in this example, let's take discharge of a river. So these are daily discharge values in cubic feet per second, which range from a low of 17 cubic feet per second to a high of, let's see, 48 cubic feet per second. And what I want to do is estimate the exceedance probability of discharges of various sizes. So specifically what I want to do is to estimate the exceedance probability, which is defined as the probability that the discharge will equal or exceed a specific value of Q. For example, I might want to know what is the exceedance probability. Let me move this over here. What is the exceedance probability of a discharge that is greater than or equal to 20 cubic feet per second? Now that might be really useful information, right? Let's say it matters to people who use the river for recreation, right? Let's say that for rafters, that if the discharge is less than 20 cubic feet per second, they can't use the river because they'll be hitting rocks. So in order to go rafting, they need to know that the discharge is exceeding 20 cubic feet per second. Or it might be important to farmers. It might be that legally they're not allowed to take water out of the river to use as irrigation water unless the river's carrying at least 20 cubic feet per second. So they want to know, hey, what percentage of the time is the river going to be carrying at least 20 cubic feet per second? What is the probability that the river is going to carry 20 cubic feet per second or more? That's information that I really want to know. So our task is, how do we estimate that exceedance probability for various discharges of the river given this small data set, this small sample of data? In this case, it consists of just 9 values. In particular, what I want to show you what we can do is to estimate the exceedance probability for these specific values. Now, let's think a little bit about how we might go about that. So let's think about the very smallest discharge that we observed in our 9 days, and that was one of 17 cubic feet per second. So we might say that the exceedance probability for a discharge of 17 cubic feet per second, we might say that we can estimate that by saying, well, this happened, this discharge was exceeded every single day, equaled or exceeded every single day, right? So all 9 days, over 9 chances of it happening, and using that kind of logic, that would infer that the probability that a discharge equals or exceeds 17 cubic feet per second is 100%, where it's a sure thing. Now, obviously that's an overreach, right? There's no way that we can actually be that sure, because we only have 9 days worth of data, and there may very well be at other days discharges smaller than that. And so during those, when the discharge is smaller than that, then it can't have a discharge equal to or greater than 17 be 100%. So this is actually not a correct formula to use, because it leads to this sort of overreach statistically. Instead, we're going to use the following method to estimate the exceedance probability for all of these different discharges. And the method starts like this. We're going to first identify the rank of each of these discharges. We're going to call the rank M, and we're going to rank these discharges from 1, the largest, down to, in this case, 9, the smallest. So there they are, the ranks, with the number 1 being the 48 cubic feet per second and our 17 cubic feet per second being the smallest at rank number 9. And then we will define the exceedance probability as follows. The exceedance probability for an event of specific discharge Q is equal to the rank of that discharge, M, divided by N plus 1, where N is the number of observations, which in this case is equal to 9. So in this example, then, we would say that the probability, I'll just put an arrow here, so the probability of a discharge that equals or exceeds 17 cubic feet per second, that's the smallest one in our 9 days, right, would be equal to its rank, which was 9, it was the smallest, divided by 9 plus 1, or 10, giving us an exceedance probability of 90%. And this is a lot more palatable, right? I mean, we only have 9 days worth of data, so there certainly will be smaller discharges in the future, and we can therefore, I mean, this was still the smallest in 9 straight days, so we can be pretty sure that it's going to be equal to or exceeded about 90% of the time. Now notice a really cool thing about this in that it automatically scales the certainty with which we can conclude that the smallest discharge in our set is equal to or exceeded. So for example, let's just do an example. Let's say we happen to have, let's say we have 1,000 days worth of data. We've collected data for nearly 3 years. We have 1,000 days worth of data. Using this method, then the probability of the smallest discharge observed in those nearly 3 years will be equal to its rank, which is 1,000. It was the smallest in 1,000 of them, divided by n plus 1, or 1,001. And that number is not quite 1, but it's close. It's about 99 point, I'm writing it here as a fraction, okay, which is about 99.9%, right? Just to be clear, right? This is 90 is 0.9. I'm just using the alternative ways of writing percentage, right? So 99.999 is 99.9%, something like that. So we're almost 100% sure that that whenever we look at the river, we're going to see a discharge equal to or larger than the smallest one we saw in 3 years, nearly 3 years. On the other hand, let's do another example here. What if we only had 3 days worth of data, just 3 days worth of data? In that case, we'd estimate the probability of the smallest one as the rank of the smallest one, which is 3, there were only 3 days, divided by n plus 1, or 4, and that is 0.75, or 75%. So what we'd be saying is that in that 3 days, the smallest discharge we observe is, we estimate, going to be equal to or exceeded 75% of the time. There are going to be a lot of other smaller events that fill in that bottom 25%, but we can sort of estimate that the smallest one in that 3-day period is going to be equal to or exceeded 75%. And the difference between these two numbers here, 75% and 99.9%, has to do with the sample size, right? When we have a great big sample size, we have a lot more certainty that the smallest discharge represents sort of the floor. And when we have a smaller data set, then we're much less certain that the smallest observed discharge represents the floor. So it works out pretty cool in the sense that it takes into account the number of data points we're using to estimate these exceedance probabilities. So now I'll just do a couple things here. One, I want to put a big box around this because this is absolutely something you need to know how to do this, right? It's the exceedance probability of inferred from a bunch of data is the rank of a given discharge, is the rank of that discharge divided by n plus 1. Now, the final thing I want to do is mention the fact that there is an alternative way to describe the likelihood that an event will be equal to or exceeded, and that is using the return period, also called the recurrence interval. These are equal, not, okay? These are all the same. These are identical terms, just different terminology. Is often also called the exceedance interval. So all of these mean the same thing. And remember how we define that. No matter what symbol we use, let's use RI. The recurrence interval is defined as the reciprocal of the exceedance probability. So again, this is the other equation you absolutely need to learn here. And these two equations then describe alternative ways of describing the likelihood that an event will be equal to or exceeded. They convey exactly the same amount of information, no more, no less, right? They're just different ways of saying the same thing. One expresses the exceedance probability as a probability. The other describes it as a return period, or the average time between events that equal or exceed a given value. They say exactly the same thing in slightly different ways, but they both express essentially the same likelihood.